efficient estimation of word representations in vector space. Abstraction. We propose two novel model architectures for computing continuous vector presentations of words from very large data sets. The quality of these representations is measured in a word similarity test, and the results are compared to the previously best performing techniques based on different types of the neural networks. We observe large improvement in accuracy and much lower additional cost. That is, it takes less than a day to learn high-quality word vectors from a 1.6 billion word dataset. Furthermore, we show we show the we show these vectors provide a state-of-the-art performance on our test set for measuring syntactic and semantic word similarities. Introduction. With many current NLP (natural language processing systems) and techniques treat words as atomic units, there is no notion of the similarity between words, as these are represented as indices in a vocabulary. This choice has several good reasons: simplicity and robustness, and the observation that simple models trained on huge amounts of data outperform complex systems trained on less data. An example is popular N-gram model used for a statistical language models. Today, it is possible to train N-grams on virtually all available data, trillion of the words. However, the simple techniques are at their limits in many tasks. For example, the amount of relevant in-domain data for automatic speech recognition is limited. The performance is usually dominated by the size of the high-quality transcribed speech data, often just millions of words. In machine translation, and the existing corpora for many languages contain only a few billion of the words or less. Thus, there are situations where simple scaling up of the basic techniques will not result in any significant process, and we have to focus on more advanced techniques. With progress of machine learning techniques in recent years, it has become possible to train more complex models on a much larger data set, and typically outperform the simpler models. Probably the most successful concept is to use distributed representation of words. For example, neural network-based language models significantly outperform N-gram models. Goal of the paper 1.1.1 Goal of the papers. The main goal of this paper is to introduce techniques that can be used for learning high-quality word vectors from the huge data set with billions of words and billions of the words in the vocabulary. As far as we know, none of the previously proposed architectures has been successfully trained on more than a few hundred of millions of the words, with a modest dimensionality of the word vectors between 50 to 100. We use recently proposed techniques to measuring the quality of the resulting vector representations, with the expectation that not only will similar words tend to be close to each other, but that words can have a multiple degree of similarity. This has been observed earlier in the context of inflection languages. For example, nouns can have multiple word endings, and if we search for similar words in the subspace of the original vector space, it is possible to find a word that has similar endings. Somewhat surprisingly, it was found that the similarity of a word presentation goes beyond simple syntactic regularities. Using a word offset technique where simple algebraic operations are performed on the word vectors. It was shown, for example, the vector king and vector man plus vector women result in a vector that is closest to the vector representation of the word queen. In this paper, we try to maximize the accuracy of this vector operation by developing a new word architecture that preserves the linear regularities among words. We designed a new comprehensive test set for the measuring both syntactic and semantic regularities, and show that many such regularities can be learned with a high accuracy. Moreover, we discussed how the training time and accuracy depends on the dimensionality of the word vectors and on the amount of the training data. 1.1.2 is the previous work. Representation of the word as a continuous. 1.2 vectors has a long history. A very popular model architecture for estimating neural network language model NNLM was proposed in number one paper, where a feed-forward neural network with a linear projection layer and a non-linear hidden layer was used to learn jointly the word vector representation and a statistical language model. This work has been followed by many others. Another interesting architecture of NNLM was presented in 13 and 14, where the word vectors are first learned using neural network with a single hidden layer. The word vectors are then used to train the NNLM. Thus, the word vectors are learned even without constructing the full NNLM. In this work, we directly extend this architecture and focus just on the first step, where the word vectors are learned using a simple model. It was later shown that the word vectors can be used to significantly improve and simplify many NLP applications. Estimation of the word vectors itself was performed using a different model architectures than trained on various corpora, and some of the resulting word vectors were made available for future research and comparison. However, as far as we know, these architectures were significantly more computationally expensive for training than the one proposed in 13. With the except of the certain version of the long bilinear model where diagonal weight matrices are used in 23. 2. Model architectures. As many different types of the models were proposed for estimating continuous representation of the words, including the well-known latent semantic analysis (SLA) and the latent Dirichlet allocation (LDA). In this paper, we focus on distributed representation of words learned by neural networks, as it was previously shown that they perform significantly better than a LSA for preserving the linear regularities among words 20 and 31. And the LDA, moreover, becomes computational very expensive on large data sets. Similar to 18, to compare different model architectures, we define the first, the computational complexity of a model as the number of parameters that need to be accessed to fully train the model. Next, we will try to maximize the accuracy while minimizing the computational complexity. For the for all the following models, the train complexity is proportional to O E times T times Q, where E is the number of the training epochs, T is the number of the words in the training set, and Q is defined further for each model architecture. Common choice is E equal 3 minus 50 and T up to 1 billion. All models are trained using stochastic gradient descent, and back propagation. 26. 2.1 Feed-forward neural network language models NNLM. The probabilistic feed-forward neural network language model has been proposed in first. It consists of input, projection, hidden, and output layers. At this layer and previous words are encoded using a one of V coding, and the V is size of the vocabulary. The input layer is then projected to a projection layer P that has dimensionality n times t using a shared projection matrix. As only n inputs are active at any given time, composition of the projection layer is a relatively cheap operation. The NNLM architecture becomes complex of the computation between the projection and hidden layer, as values in the projectional layers are dense. For a common choice of n equal 10, the size of the projection layer P might be 500 to 2000, while the hidden layer size H is typically 5000 or 500 to 1000 units. Moreover, the hidden layer is used to compute probability contribution over all words and the vocabulary. It's resulting in an output layer of the dimensionality V. Thus, the computational complexity per each training example is Q equal n times D plus n times D times H plus H times V, where the dominating term is H times V. However, several practical solutions were proposed for avoiding it, either using a hierarchical version of the softmax or avoiding normalized models completely by using models that are not normalized during training. With binary tree representation of the vocabulary, the number of output units that needs to be evaluated can be down around log 2v, that the most of the complexity is caused by the term n times d times h. In our models, we use hierarchical softmax where the vocabulary is represented as a Huffman binary tree. This follows previous observation that frequency of word works well for obtaining classes in neural net language models. Huffman trees assign short binary codes to frequent words, and this further reduces the number of the times output units that need to be evaluated, while the balanced binary trees would require log 2 v have to be evaluated. The Huffman tree is based on hierarchy softmax requires only about log 2 and unigram is perplexity. For example, when the vocabulary size is one of the billion words, this results in about 2 times speedup in the evaluation. While this is not a crucial speedup for a neural network LM, the computational bottleneck is in an n times d times h term. We will later propose architecture that do not have hidden layers and thus depend heavily on the efficiency of the softmax normalization. 2.2 is recurrent neural network language models, RNNLM. Recurrent neural network-based language model has been proposed to overcome the certain limitation out of feed-forward NNLM, such as the need to specify the context length, the order of the model n, and because theoretically RNNs can be efficiently represent more complex patterns than shallow neural networks. The RNN model does not have a projection layer, only input, hidden, and output layer. What is special for this type of model is the recurrent matrix that connects hidden layer to itself using time-delayed connections. This allows the recurrent model to form some kind of short-term memory, as the information from the past can be represented by the hidden layer state that gets updated based on the current input and the state of the hidden layer in the previous time step. The complexity per training example of the RNN model is Q H times H plus H times V. The word presentation D have the same dimensionality as hidden the layer H. Again, the term HXV can be efficiently reduced to HX times log 2V by using a hierarchical softmax. Most of the complexity then comes from the H times H. 2.3 Parallel training of the neural network. To train models on user data set, we have implemented several models on the top of a large-scale distributed framework called DistBelief, including the feed-forward NNLM and the new models proposed in this paper. The framework allows us to run multiple replicas of the same models in the parallel. Each replica synchronizes the ingredient updates and throughout the naturalized server that keeps our parameters. For this parameter training, we use the mini-batch asynchronous gradient descendant with a adaptive learning later procedure called Adagra. As under this framework, it's common to use the 100 or more model replicas, each using many CPU model cores at different machines in data center. 3. New log linear models. In this section, we propose two new model architecture for learning distributed representations of the word that try to minimize computational complexity. The main observation from the previous section was the most complexity caused by the nonlinear hidden layer in the model. While this is what makes neural networks too attractive, we've decided to explore simpler models that might not be able to represent the data and precisely as neural networks, but can possibly be trained on much more data efficiently. The new architectures directly follow those proposed in early work, there where it was found that a neural network language model can be successfully trained in two steps. First, continuous word vectors are learned using a simple model, and then the n-gram NNLM is trained for top of these distributed representation of the word. While there has been a later substantial amount of work that focuses on the learning word vectors, we consider the approach proposed in 13 to be the simplest one. Note that the related models has been proposed also much earlier. 3.1 Continuous bag-of-word model. The first proposed architecture is similar to a feed-forward NNLM, where the nonlinear hidden layer is removed from the projection layer is shared for all words, not just to the projection matrix. Thus, all words get projected into a same position. Their vectors are averaged. We call this architecture a bag-of-word model as the border of the words in history does not influence the projection. Furthermore, we also use words from the future. We have obtained the best performance on the task introduced in next section by building a log linear classifier with 4 future and 4 history words at the input, where the training criterion is correctly classify the current middle word. Training complexity is then Q equal N times D plus D times log 2V. We denote this model for the CBOW as unlike a standard bag-of-word model, it uses continuous distributed representation of the context. This model architecture is shown in Figure 1. Note that the weight matrix between the input and the projection layer is shared for all word position in the same way as in the NNLM. 3.2 3.2 Continuous Skip-gram model. The second architecture is similar to CBOW, but instead of predicting the current word based on the context, it tried to maximize classification of a word based on another word in the same sentence. More precisely, we use each current word as an input to log linear classifier with a continuous projection layer, and the prediction words within a certain range before and after the current word. We found that increasing the range improved the quality of the resulting of vectors, but it also increases the computational complexity, since the more the distance words are usually less are related to the current word than those close to it. We give less weight to the distance word by sampling less from those words in our training example. The training complexity of this architecture is proportional to Q equals C times T plus D times log 2V, where the C is maximum distance of the word. Thus, we choose C5, C5, Seeker 5. For each training word, we will select randomly a number R in range 1 to C and to the use R words from history and R words from the future of the current word as correct label. This will require us to do R times 2 word classification with the current word as input and each of the R plus R words as output. And the following experiment we use C equal 10. The figure 1 is new model architectures. The CBOW architecture predicted the current word based on context, and the Skip-gram predicted surrounding words given the current word. 4. Result. To compare the quality of the different versions of word vectors, previously papers typically use a table showing example words for n. They are both similar words and understand them intuitively. Although it is easy to show that the word France is similar to Italy and perhaps some other countries, it is much more challenging than subjecting those vectors in a more complex similarity task. As follows: we follow previous observation that there can be as many different types of similarity between words. For example, word big is similar to a bigger to a same sense than a small is similar to the smaller. Example of the another type of the relationship can be word pairs big and biggest and smallest. We found denoted two pairs of words the same relationship as the second as a question, as we can ask what is the word that is similar to the small and the same sense as biggest is similar to big. Somewhat surprisingly, this question can be answered by performing the simple algebraic operations with a vector representation of words. To find a word that is similar to a small in the same sense as the biggest to similar to big, we can simply compute vector x vector biggest minus vector big plus vector small. Then we search the vector space for the word closest to x measured by cosine distance and use it as the answer to the question we discovered the implication was during this search. When the word vectors are well trained, it is possible to find the correct answer, word smallest using this method. Finally, we found that we trained the high-dimensional as word vectors on a large amount of data. The resulting vectors can be used to answer various subtle semantic relationships between words, such as a city and the country it belonged to. For example, France is to Paris as Germany is to Berlin. As word vectors with such semantic relationships could be used to improve many existing NLP applications, such as machine translation, information retrieval, and question answering systems, and may enable other future applications yet to be invented. Table 1 is an example of 5 types of semantic and 9 types of semantic question in semantic syntactic word relation test set. Types of relationship and word pair and word pair 2. 4.1 is task description. To measure the quality of the word vectors, we define a comprehensive task set that contains 5 types of the semantic questions and 9 types of the syntactic questions. 2 examples from each category are shown in Table 1. Overall, there are 8,869 semantic and 10,675 syntactic questions. The questions in each category were created in 2 steps. First, a list of similar word pairs was created manually. Then the large list of questions is formed by the connecting 2 word pair. For example, we made a list of 68 large American cities and the state they belonged, and formed about 2.5 kilo questions by picking 2 word pairs at random. We have included our test set only single token words, thus multi-word entity are not present, such as New York. We evaluate the overall accuracy for question types. For each question type separately, semantic and syntactic. Question is assumed to be correctly answered only if the closest word to the vector computed using the above method is exactly the same as the correct word in the question. Snow means that that's counted as a mistake. This also means that reaching 100% accuracy is likely to be impossible, as the current models do not have any information about word morphology. However, we believe the usefulness of the word vectors for certain applications should be positively related with this accuracy metric. Furthermore, a further progress can be achieved by the incorporating information about the structure of words, especially for syntactic questions. The maximization of accuracy. We have used the Google News corpus for training the word vectors. This corpus contains about 6 billion tokens. We have restricted the vocabulary size to 1 million most frequent words. Clearly, we are facing the time-constrained optimizing problems, as can be expected. Both using more data and higher dimensional word vectors will improve the accuracy. To estimate the best choice of the model architecture for obtaining as good as possibly result quickly, we have we have first evaluated the models and trained on the subset of the training data. We've vocabulary restricted the most frequent kilowatt, the resulting using the CBOW architecture with different choice of word vectors, dimensionality, and the increasing amount of the training data are shown in table 2. It can be seen that after some point, adding more dimension and adding more training data provided diminishing improvement. So we have to increase both vectors, dimensionality, and the amount of the training data together. While the observation might seem trivial, it must be noted that it's currently popular to train word vectors on a relatively large amount of data, but the insufficient size, such as 5200, given equation 4, increasing amount of training data twice result in about the same increase of the computational complex as increasing vector size twice. For the experimental reported in table 2 and 4, we used the 3 training approach with the stochastic gradient descendant and background propagation, which shows starting the learning rate of 0.025 and decreasing linearly, And so that is approach 0 at the end of the last training approach. Epoch, not Chi. Table 2. The accuracy on a subset of a semantic word semantic synthetic word relationship test set using word factors from the CBOW architecture with the limitation vocabulary. Only questions containing words from the most frequent 3 keywords are used. The comparison of the architecture using models trained on the same data with the 604-dimensional word vectors, the accuracy reported on the semantic-synthetic word relationship test set, and on the synthetic relation test set of 20. 3.3 4.3 Comparison model architectures. First, we compare the different model architectures of deriving the word vectors using the same training data and using the same dimensionality of 640 of the word vectors. And for the experiment, we use full set of location in the new semantic synthetic word relationship test set that is unrestricted to the 30 vocabulary. We also include the resulting on a test set introduced to training that focuses on a syntactic similarity between words. The training data consists of several LDC corpora and it describes the detail in a 618, 320 megawords and 82 kilo vocabulary. We use these data to provide a comparison to previously trained recurrent neural network language model. The two were 8 weeks to train on a single CPU. We trained a feed-forward NNLM with the same number of 64 hidden units using the distinct belief parallel training using a history of 8 previous words, such as the NNLM has more parameters than a RNNLM, as the projection layer has a 600 400 times 8. In Table 3, it can be seen the word vectors from RNN, such as 20, performed well are mostly the semantic questions. The NNLM vectors perform significantly better than RNN. RNN, this is not surprisingly, as the word vectors in the RNNR are directly connected to a non-linear hidden layer. The CBOW architecture works better than NNLM on the semantic tasks, and about the same on the semantic one. Finally, Skip-gram architecture works slightly worse than a syntactic task than a CBOW model, but still better than an NLM and much better than a static part of the test that all the other models. Next, we evaluate our models trained using one CPU only and compare the results against publicly available word vectors. The comparison is given in Table 4. The CBOW model was trained on the subset and of Google News data in a day. We trained for Skip-gram models was about 3 days. So the table 4 is comparison of publicly available word vectors of semantic synthetic word relationship test set and word vectors from our models. 4 vocabularies are used. Table 5 is a comparison of models trained for 3 epochs of the same data and models trained for 1 epoch. Accuracy is reported on the full semantic synthetic dataset. For experiment reported further, we used just one training epoch. Against we increased the learning rate linearly so that it approaches 0 at the end of training. Training a model twice as much data using the one epoch gives comparable for or better result than iterating over the same data from 3 epochs, as is shown in Table 5, and provide additional small speedup. 4.4 A large-scale parallel training of the models. As mentioned earlier, we have implemented various models in a distributed framework called disbelief. Below we report the result of the several models trained on a Google use 6 billion dataset with the mini-batch asynchronous gradient descendant and the adaptive learning rate procedure called ADA-GRAD. We used 5,200 model replicas during the training. The number of the CPU cores is an estimated since data center machines are shared with other production tasks, and usage can be fluctuated quite a bit. Note that Note that due to the overhead of a distributed framework, the CPU usage of the CBOW models and Skip-gram models are much closer to each other than their single machine implementation. The result are reported in Table 6. In Table 6 is a comparison of the models trained in this distributed framework. Note that the training of the NNLM of the 1,000-dimensional vectors would take long to complete. Comparison and computational models at the Microsoft Sentence Completion Challenge. 4.5 is a Microsoft Research Sentence Completion Challenge. The Microsoft Sentence Completion Challenge has been recently introduced as a task for advancing language models and other NLP techniques. This task consists of 1,004 sentences where one word is missing in each sentence, and a goal is to select word that is most current with the last of sentence, given a list of 5 reasonable choices. Performance of several techniques has been already reported on the set, including n-gram models, LS-based models, local bilinear models, and a computational and a recurrent neural network that currently hold the state-of-the-art performance of the 54.5% 55.4% accuracy on this benchmark. We have explored the performance of the Skip-gram archived on this task. First, we trained the 604-dimensional models on 50 million words provided in 32. Then we compute score of each sentence in the test set by using the unknown word at the input and predict all surrounding words and a sentence. The final sentence score is then a sum of these individual predictions. Using the sentence scores, we choose the most likely sentence. A short summary of some previous results together with the new result is presented in Table 7. While the Skip-gram model itself does not perform the on-task validation LSA similarity, the scores from the model are complementary to scores obtained with the RNNLM, and the weighted combination leads to a new state-of-the-art result to 58.9% accuracy as 59.2% of the development part of the set and 58.7% of the test part of the set. 5 is the example of the long relationships. Table 8 shows the word data follow the various relationships. We follow the approach described above. The relationship is defined by subtracting two word vectors, and the result is added to another word. Thus, for example, Paris minus France plus Italy as long as can be seen, accuracy is quite good. Although there is clearly a lot of room for the further improvement, note that using a arXiv metric that assumes that exact match. The result is Table 8 would score only about 60%. We believe that the word vectors trained on an even large dataset as a large dimensionality will perform significantly better and will enable the development of the new innovation application. Another way to improve accuracy is to provide more than one example of the relationship. By using the example instead of one to the form of the relationship vectors, we average the individual vectors together. We have observation from the accuracy of our best models about 10% absolutely, absolutely on the semantic synthetic set. It's also possible to apply the vector separation to solve different tasks. For example, we have observed good accuracy for selecting out of listed words by computing average vectors for a list of the word and finding the most distant word vector. This is a popular type of the problem in certain human intelligence sets. Clearly, there is still a lot of discoveries to be made using these techniques. And the table 8 is examples of the word pair relationship using the best word vectors from table 4. Skip-gram model trained at 783 billion words and with a 300 dimensionality. Conclusion. In this paper, we studied the quality of the vector representation of a word derived by various models on a collection of synthetic and semantic language tasks. We observed that it's possible to train the high-quality word vectors using very simple model architectures. Compared with the popular neural network models, both feed-forward and recurrent. Because of the much lower computational complexity, it is possible to compute very accurate high-dimensional word vectors from a much larger dataset. Using this distributed framework, it should be possible to train the CBOW and Skip-gram models even on a couple with 1 trillion words that for basically unlimited size of the vocabulary. That is several orders of magnitude larger than about previously published results for similar models. An interesting task where the word vectors have recently been shown to the significant perform the previous state of the art is the SAM-EVAL 2012 Task 2, and the publicly available RNN vectors were used together with our techniques to achieve the over 50% increase in the experiment's rank relationship of the previous best result. And the neural network based on word vectors were previously applied to other NLP tasks, for example, semantic analysis 12 and a paraphrase detection 28. It can be expected that this application can benefit from the model architectures described in this paper. Our ongoing work shows that the word vectors can be successfully applied to automatic extension of the fact in knowledge base and also verification of correctness of the existing facts. Results from the machine translation experiment also look very promising. As in the future, it would be also interesting to compare our techniques to latent relation analysis and others. We believe that our comprehensive test set will help the research community to improve the existing techniques for estimating the word vectors. We are also expecting the high-quality word vectors will become an important building block for future NLP applications. The follow work. After the initial version of this paper was written, we published a single machine multi-threaded setup plus code for computing the word vectors and using both continuous bag of words and skip-gram architectures. The training speed is significantly higher than reported earlier in this paper. That is, it is very in order to billions of words per hour for typical hyperparameter choices. We also published more than 1.4 billion vectors that represent named entities, trained one more than 100 billion words. Some of our follow-up work will be published as upcoming NISP 2013 papers, and there are many references. Thank you for your time today, and see you next time. Thank you.